Try to, maybe I'll use this board that's, well, if I erase it with a wet eraser, I won't be able to write on it for a few minutes. Okay, so have you turned the thing on?
Mm-hmm.
Oh, all right. So basically, the answer to your question, I think, is this, that something like this, phi 0 can be written as a constant e to the minus something like a half square root of p squared plus m squared dqp, something like that.
Okay.
And let me just,
Yeah, that's 16,132.
good, 16, right, plot from a 2 pi cube. Oh, and of course, most importantly, phi tilde prime of p squared, and of course a 2 pi cube. All right, and the idea was there was a prime here. This is just a function of space, and this is the Fourier transform of that function of space.
Okay.
And
Anyways,
so the point is we can write that what we were doing here was writing that as C e to the I delta S. And
oh,
okay,
yes, I missed that step.
so then delta S is I over 2, the I is giving the minus sign, and integral square root of p squared plus m squared, and then phi prime tilde of p and t. This just indicating that we have, we're imagining that between the function at the function phi, the field phi at t and at minus t, the some function that interpolates, in which case this, when t is plus infinity, it's the one, when t is minus infinity, it's the other. Okay. All right, any other questions? Let me pay the unpaid TA. Okay, so we were at the point where I had defined functional derivatives for you, right? But I don't think I had actually applied it to this business. Okay, so let's notice first of all that we had gotten this result, which is rather interesting, namely that this is 0 time ordered product e to the I integral j phi d4 of x, that this is equal to e to the I over 2 integral and j of x delta of x minus x prime j of x prime d4 of x d4 x prime. And of course in here we have an x and an x. Okay. And so let's do one of these carefully. Let's compute 1 over I, the variational derivative of this functional with respect to j of x. And let me try to do this explicitly so that everything is all right. So what we're actually saying here is that this is 1 over I dd epsilon of z0, and now if I write this function explicitly, it's j of x prime, let us say, plus epsilon delta of x prime minus x. So that's what we mean by this variational derivative. And then we set epsilon equals 0. Well, if we do that in this left-hand side, what we're doing is 1 over I d by d epsilon of vacuum time-ordered product EVI integral, and now it's let me make that j of x prime. So it's j of x prime plus epsilon delta x prime minus x phi of x prime d4 of x prime. And now we take d by d epsilon of that, and that brings down the i's cancel, and so we get 0 time-ordered product. All we have left is phi of x prime, or actually we have integral phi of x prime delta x prime minus x d4 of x prime, and then e to the I integral, and setting epsilon equal to 0, we just have, say, g of x prime, b of x prime, d4 of x prime, and the time ordering vacuum. And now when you do the d4 of x prime integration, you just get phi of x. And so this is 0 time ordered product phi of x e to the I integral. Is it I or I? Let me just write it as d2, j phi d4 of x like that. So that's the left-hand side. The right-hand side is a little bit trickier because it is 1 over I d by d epsilon of e to the I over 2. And now what we'll have is j of x plus epsilon delta of, well, j of x prime. I'll make this prime and make this double prime. So it's delta of x prime minus x, delta of x prime minus x double prime, and then j of x double prime plus epsilon delta of x double prime minus x. And then d4 x, d4 x prime, d4 x double prime. These blackboards, I used to think they were really great blackboards, but they're not as good as the ones in room 5, the new ones. On the other hand, these blackboards are like 40 years old. So. Okay, so let's do the d by d epsilon here. Obviously the i's cancel, and so we get a 1/2 integral delta of x prime minus x, delta of x prime minus x double prime, and then we can just let this be j of x double prime, d4 of x prime, d4 of x double prime for the derivative with respect to this epsilon. And then with respect to that epsilon, we get another factor of 1/2 is delta of x double prime minus x. And then over there, j of x prime, delta of prime minus x double prime, d4 of x prime, d4 x double prime. And so now the integration over x prime just replaces x prime with x, and so what we get is an integral delta of x minus x double prime, j of x double prime, d4 x double prime, with a half, but on the other hand, over here, the integral over x double prime just gives us j of x delta of x prime minus, so maybe if I put them both in there, I'll do it this way, plus a half integral j of x prime delta of x prime minus x d4 x prime. And now we see these two integrals are actually the same, and so the result is then j of x prime delta of x prime minus x d4 x prime, and the 2 cancels. So that's the way all of this stuff goes. All of these derivatives with respect to, all of these functional derivatives are like that. Okay. Now, unfortunately, they get more and more cumbersome, and you just have to keep track of everything. So you basically hire a secretary to do that, or you do it yourself. So let me show you what the second derivative is. In fact, if we do 1 over I squared, the second derivative of z of j, z0 of j. Yeah, I sometimes, I guess, drop the 0. 0 means we're talking about the free theory. If we now do that, what we get is on the one hand, 0 time ordered product of phi of x prime and of course, I should say, we're doing all this normally at j equals 0. So there are 2 equals 0 things. One is what the functional derivative is, and then after we finish, we're doing this at j equals 0. And when we said j equals 0, you see, this thing just, the exponential just becomes 1, and then over here we get 0. And that would just say the mean value of the field is 0, which is true because the action is quadratic, and so the mean value of the thing, it's like the mean value of x if you integrate from minus infinity to plus infinity. So the second derivative is then that at j equals 0, and the answer here is minus I delta of x minus x prime. Now, why is, so I've just written this down, but we can in fact derive it from this relation. In other words, we can take the functional derivative of this equation with respect to j of x prime, and then that will give us delta, and on the other hand, over here, it will give us another phi. So in other words, if we do it rigorously, it takes, a lot of chalk. But if we just do it the old physics way, we think of this thing here as, Well, you can just imagine that the whole thing's on a lattice and we're just differentiating with respect to phi, j of x prime in some hypercube. If you differentiate, what do you get? You just get delta, and then over here, you differentiate and you just bring down another phi. So this thing, in other words, gives you directly that. All right. Now, and of course, this is a very nice result. This tells us that the Feynman propagator is this delta of x minus x prime, and we know what that is, namely it's a four-dimensional Fourier transform of 1 over p squared plus m squared minus I epsilon. Did I write that down? Okay. It's equation 16.149. So that's the formula, and okay, well, if we continue in this way, and in other words, if we had written this thing down not at j equals 0, but it kept j finite, we could differentiate 2 more times. And then what we would find would be that the time-ordered product of phi of x1, phi of x2, phi of x3, phi of x4 in the vacuum is 1 over I to the fourth functional derivative of z0j with respect to j of x1, j of x4 at j equals 0, and this in fact is equal to minus delta of x1 minus x2 delta x3 minus x4 minus delta x1 minus x3 delta x2 minus x4 and minus delta of x1 minus x4 delta of x2 minus x3. So it's a product of propagators. That's what the 4-point thing is. All right, I don't think you want me to try to derive that because it's not hard. It's just a lot. But I mean, if you really want it, I'll try to do it. But it's an awful lot of chalk. Okay. So now, so far we've been just talking about this free theory, but of course you can add a potential. You can say that this potential is some polynomial in the fields, and then the scattering. This then would be the interaction Hamiltonian, or the interaction Hamiltonian. And scattering amplitudes, you know, from time-dependent perturbation theory, are essentially time-ordered products of e to the minus I integral of the interaction Hamiltonian, which in this case is p of phi d fourth x. So scattering amplitudes would be given by, well, this is the operator. And what you do is you populate the states with you want to have states of different momenta, initial states, and maybe two incoming particles and 2 or 3 outgoing particles. And so what we get for this would be an integral of e to the minus I p T of phi d4 x e to the I S0 of phi d phi divided by integral e to the I S0 of phi d phi. So in other words, here, I mean, what we've developed is the time-ordered product of anything is, in the free theory, is that thing in this path integral. And now that thing happens to be a an exponential polynomial to give us the interaction Hamiltonian. And so this is an exact formula for that. And then the next thing, which people who really like functional derivatives, and I think it's almost magic, they write it this way. They say, well, we know how to generate this P of phi. Anytime we want a phi, all we do is functionally differentiate with respect to J0. All right. So what we do is we say, aha, this thing is in fact, in other words, just as, so let me give you the just as. I'm trying to find the just as. Okay, just as a time-ordered product of two fields is a double functional derivative of J0, of Z0 of J at J equals 0, so too, the time-ordered product of this thing, which is almost impossibly complex, is a certain functional derivative. What is the functional derivative? Well, it is e to the minus I integral P of d of I, the functional derivative with respect to J of x, d4 of x. It's that thing acting on Z0 of J, and then you set J equals 0. So in other words, this thing acting on that turns into a phi, and then you're done. Of course, this is a mind-boggling thing. Some people really get a perverse joy out of that, and I think it's pretty frightening expression. By the way, the path integral formula in interacting theory, we go to a fully interacting theory, then we have the vacuum of the ground state of the full theory. We have the time-ordered product of these fields, and now we mean fields evolving with the full Hamiltonian, as opposed to the, over there we had just free field theory. This is then equal to, it's still a ratio of path integral, phi of x1, phi xn, e to the I s of phi and epsilon, I'll say what epsilon is in a minute, divided of course by e to the I s phi epsilon d phi. And now this phi, the epsilon means that in other words, s of phi and epsilon is s of phi plus I epsilon integral of phi squared, say, d4 of x. So this essentially is this together with that I gives you damping at very large times and so forth.
Wi-Fi.
Let me put this in quotes. I mean, I haven't thought out exactly what the form of that is, but it's just a repetition for the interacting theorem of Weinberg's argument that gave us the I epsilon and the propagator. Okay. All right, now, the next topic is to give you an example of this. In particular, let's think about QED. Now, in quantum electrodynamics, as in any gauge theory, there's a constraint. And these constraints caused a sort of mental crisis in physics, and as usual, most mental crises were solved by Dirac. And this Dirac solution is the Dirac brackets. I'm not going to go through this. I'll just refer you to Weinberg, Volume 1, and it's pages 413 to 418. So that's 5 or 6 pages of pain there, where he discusses the Dirac brackets. And let me give you the sort of, let's see, did I bring my notes on this topic? Hold on. No, of course, I forgot them. All right, so I will give you a very, I'm not going to do the Dirac bracket, but what I'll do is show you roughly what's going on. So the Lagrange density is this. It's E squared minus B squared. And then you would have a J mu, A mu, a term like that, where the J is the matter current. And now what you see here, first of all, what's the constraint? Well, the constraint is that you see, you first want to find your canonical momentum, or momenta, conjugate to each of these fields. And in particular, for I equal 1 to 3, this is just partial of L with respect to AI dot. And that is effectively EI. On the other hand, A0 doesn't have a time derivative in the action density. And so that means that pi 0 is 0. So that's the constraint. Moreover, this constraint has a brother, which is when you look at Lagrange's equations will give you essentially the gradient or the divergence actually. Well, let me just do it for you. It's Lagrange's equations are d mu partial L partial A0, say, comma mu is equal to partial L partial A0. Well, partial L partial A0 here is J0, which is the charge density. This thing is only non-zero for spatial values of mu. And so this means we have something like a divergence of, and what's the derivative with respect to A0 comma I? Well, it's EI. And so this is that the divergence of E is equal to J0. And that's Gauss's law. But this is also a constraint. So we have two constraints, C1 and C2. And Dirac showed us how to handle these. As I say, I refer you to Weinberg. But the long and short of it is, well, the easiest way to proceed, and the most physical way to proceed, is to say, well, we're going to go to Coulomb gauge, and in particular, we're going to impose, well, yet another constraint, namely that del dot A is 0. And then we're going to say, well, we have here that this is del dot E equals J, but in fact, this thing is actually something like minus Laplacian of A0 equals J0. And so therefore we can write this funny field A0 as 1 over 4 pi, an integral J0 of y d cubed y over x minus y. So this is the instantaneous Coulomb potential. And this has a marvelous effect because it means that we don't need to quantize this thing. Because it's just, we just replace it everywhere by an integral over the charge density. And the charge density is defined in terms of the matter field, the charge fields. So what do we quantize? Well, we've already gotten rid of the longitudinal degree of freedom of the, so we only quantize the transverse degrees of freedom. So that's basically it. And then we find that the Hamiltonian then is the matter Hamiltonian plus an integral, and of course it's a half pi squared, and then minus L essentially. And minus L means we have B squared, which is a half curl of A squared, and then minus A dot J d cubed x. So A dot J is the 3-vector part of that. Then the A0 thing, we get rid of A0 completely, so we just have J0 times an integral of J0, and that's what's called the Coulomb term. So I'm just going to write that as Coulomb potential, where Vc is an integral of J0 of x and t, J0 y and t, d cubed x, d cubed y over 4 pi x minus y. Okay, this is all apparently non-relativistic, but in fact, the theory is Lorentz invariant. Okay, so that's our Hamiltonian, and once again, Weinberg actually, I'm not sure that, anyway, Weinberg discusses the Dirac brackets. Whether it's here or somewhere else, I don't actually remember, because I didn't look at them today. In any event, what you find is that analogous to the formulas we were deriving for the scalar case, what we have now is ground state time-ordered product operators O1 to ON. And initially, these are any old operators, but pretty soon we're going to restrict ourselves to gauge invariant operators. So it's the classical version of these things. E to the I S sub C, a functional delta function imposing the Coulomb gauge, and then we integrate over the three components, the space components of the electromagnetic field. We integrate over the matter field, and then we divide by the same thing, SC delta of del dot A, dA, d psi. Okay, so that's what you get in the end, and this delta function, delta functional, so this is a product over all space-time points, of the ordinary delta function. So that's a pretty serious delta function. Okay, so, and what is this SC? Well, SC is the Coulomb gauge action, which is a half A dot squared minus a half curl A squared plus A dot J plus whatever the action density is in the matter fields, E4 of X, and then minus a time integral of this Coulomb term, which is over here. Now, let me just notice something. How come E squared turned into just A dot squared? Well, the other part of E is the gradient of A0, and A0 is gone. It's just all, we solved for it and put the Coulomb term. All right, so that's basically the starting point. And in any gauge theory, you have something like this happening, although in the non-abelian case, one doesn't normally use the Coulomb gauge. The reason is that the Coulomb gauge is a nightmare in the non-abelian case. Julian Schwinger was able to sleep through that nightmare, but most people wake up and change gauge. Schwinger was never bothered by mathematical complexity. He enjoyed it. There was a rumor, I don't know if it was true, when I was a graduate student, there was a rumor that when Schwinger was younger, in other words, not in the, I was at Harvard in the mid-60s, that somehow in the early 60s or in the 50s, Schwinger would, I guess this was before Schwinger got married, he'd wander around the Harvard physics department at night and he'd see these graduate student notes where they were working on homework problems. He'd look down, he'd write down the answer, and he'd go over and he'd happen to glance at another, write down. And the students would find these magical solutions to their things that would drive them crazy. I don't know if that's true. I think it probably is true. All right, now we're going to play with this. We have this action in these two places, and this action is hopelessly, it has an appearance that's very asymmetrical. And so what we do is we introduce a fudge factor, F. And this is itself a path integral. E to the I a half grad A0 plus grad inverse Laplacian J0 squared d4 of x. That's all in the exponential, and now we have dA0. Okay, so this A0, and we've gotten rid of A0. This is just some classical field that's a mathematical trick. Because on the other hand, in path integrals, everything's a classical field. So. All right, there's A0. Again, this classical field. This is the real J0. This is the inverse Laplacian. And what is the inverse Laplacian? The inverse Laplacian is just simply minus 1 over 4 pi x minus y. That's the inverse Laplacian because Laplacian of this is minus Laplacian on 1 over 4 pi x minus y, and that's delta 4 of x minus y. So that's the sense in which it's the inverse Laplacian, this being the identity, sort of functional identity matrix. Okay. Now, what is this f? Well, after you integrate over this, it's just some number, right? At least, it's some number if we represented the J0 in a path integral as, suppose the other fields were scalar fields, then these would also be classical fields that would be functionally integrating over. So it would be some number. Okay, so what we do is and in fact, when you think about it, this F is really independent of J0 because you can shift A0 and cancel this term. So what we do is we multiply numerator and denominator by F. Okay. And as we're doing that, we notice that we can write F somewhat differently. We can write F as an integral e to the I, integral over space-time, of a half grad A0 squared. And then it's going to be, well, it turns out that it's minus A0 J0 and minus a half J0 inverse Laplacian J0 d4 x and then dA0. Okay, now I should explain why this turns out to be that. I assigned it as an exercise, but I think maybe I should do it in class because it's well, first of all, there's a cross term. What does the cross term look like? The cross term is grad A0 dotted into grad inverse Laplacian J0, and there would be a 2. Okay? All right, so if we want to get this, what we do is we integrate by parts, drop the surface term, and that gives us minus 2 A0 Laplacian inverse Laplacian J0. And, well, Laplacian, I'm sorry, inverse Laplacian, inverse A. And that's just 1, so this is minus 2 A0 J0. On the other hand, there was a 1/2 here, and so we just get minus A0 J0. The other term is this thing squared, which is a half gradient inverse Laplacian J0 gradient dotted into gradient inverse Laplacian J0 d4 x. And what is this? Well, one way of writing it is a half, well, we're integrating, so we can integrate by parts. This is gradient inverse Laplacian J0 d4 x, and now I'm going to write this somewhat more explicitly as gradient inverse Laplacian is minus 1 over 4 pi x minus y, J0 with y and x0, d cubed y. And now the next step is to integrate by parts again, and so this is 1/2 inverse Laplacian J0. This one comes over as Laplacian inverse, well, it's so it's like that, and this thing gives us a delta of x minus y. Or, no, actually, we're not going to do that. We now have the inverse Laplacian. We integrate by parts and cancel Laplacian. So this is 1/2 J0 of x d4 x inverse Laplacian 1/4 pi x minus y J0 y and x0 d cubed y. And so altogether then it's 1/2 J0 of x 1/4 pi x minus y J0 y and x0 and d4 x d cubed y. And this is what we call the integral of VC dt. So in other words, the square of this gives us a term which is right, which is simply this. And another way of writing that is e to the I integral 1/2 rad A0 squared minus A0 J0, and then this is plus I, well, d4 x say, plus I VC dt. So now what you see is that this f that we had, well, of course, d A0, functional integral there. And so we've got these two factors, and then we've got this. Now this whole thing was arranged to give us this, because plus I integral VC dt cancels when you multiply this by I minus I integral VC dt. So the Coulomb term goes away. Moreover, we get two new things that we add to the original action there. And what do we have then at that stage? What we have is that time-ordered product of these operators, O1 to ON, is O1 to ON, e to the I s prime, this huge delta function, dA d psi, where this is now all 4 a's, divided by integral e to the I s prime delta. So dA mu, if you want, to indicate that it's all 4. Where now, what is S prime? S prime has a nicer shape to it. S prime now is 1/2 a dot squared, which was there, minus curl of a squared. So that's e squared minus b squared in the Coulomb gauge. But then there is plus 1/2 rad A0 squared plus a dot j, which was always there, then minus A0 J0, and then plus the action density of the matter fields. Okay, so that's rather a nice expression because we also have this Coulomb condition. So we can add a term that's 0. And the term we're going to add that is 0 is, we're going to add the term, well, let me do it over here. We're going to add the term divergence of A dot times A0. And that's 0 because of the functional delta function that enforces the Coulomb gauge condition. On the other hand, we're going to integrate it by parts, and that gives us minus A dot rad A0. So we can add this term here, and if we combine these two together with that term, we can rewrite this thing as, we turn it into S, which is an integral of a half A dot minus grad A0 squared minus a half curl of A squared plus A dot J minus A0 J0 plus Ln C4 X. So now you see this is the fully gauge invariant, Lorentz invariant action. This is, in other words, minus a quarter FAB plus AB JB plus matter density. Okay, so the action now in the path integral is the one that, you know, that you really love, namely the one that's gauge invariant, Lorentz invariant, the classical action of the theory together with whatever the matter stuff is. So now, in order to save my writing, let me just say that now what we've got is we get to remove the prime. So in other words, this is our expression. And the only relic of the Coulomb gauge condition is this functional delta function. All right, are there any questions? Yes.
How did we get away with introducing this F factor? Because on the left-hand side, we have this time-order product term, which is exactly the same as before we introduced
Oh,
the F.
we multiply the fudge factor to the numerator and the denominator. F is just a number.
Okay. All right.
And
Okay.
we numerator and denominator cancel.
Okay.
And we had to do it in the denominator, otherwise we couldn't have eliminated this prime.
Yeah, I didn't notice that.
Okay. But I owe you a candy. And, do I owe anybody else a candy? I sometimes lose track. Now let me see, we start a quarter of an hour. All right, so we have about another 18 minutes. All right, let me get my chalk. All right, now here is where we do something interesting. And I just, this afternoon, found a slightly better, clearer way of saying it, so I've modified the online version of the book a little bit. What we're going to do is we're going to make a gauge transformation. We can make a gauge transformation in the numerator and in the denominator. And what happens? Well, first of all, let's say we're going to go restrict ourselves to gauge invariant operators. So this doesn't change. S is gauge invariant. It doesn't change, but this changes. So we can make a gauge transformation in the numerator. And what does this turn into? Let me see. It turns into plus Laplacian of lambda. So in other words, this is three-dimensional. So A prime is A plus grad lambda. And so the divergence of A is A plus Laplacian of lambda. But we're going to do a different gauge transformation here. In general different. It could be the same, but it certainly can be different. So this is del dot A plus Laplacian lambda prime. So I've got three things that I'm going to certainly confuse. There's Laplacian, which is a triangle, gradients, which is a triangle upside down, and A, which is almost a triangle, and lambda, which is almost a triangle. So, real mess. Anyway, so all we've done here is made a change of variable, so nothing has happened. We're integrating over everything anyway. All fields
including all matter fields. Okay, so we've done that. Now, well, we've got two choices. One choice that I particularly like, because it's in certain sense simple, it's more attractive, I think, is we're just gonna, not only are we gonna do this shift, but now we're gonna integrate over all gauge fields in the numerator and the denominator. Well, what happens is that blows away the direct delta function, or delta function.
And so what we get now is that this is integral O1 to On e to the I as dA d psi divided by e to the I as dA d psi. So now we're integrating over all gauge fields, all matter fields, and since we're integrating over all gauge fields, we're effectively also integrating over all gauge transformations because, yeah, one thing I sloughed over here somewhat casually is I forgot to say that our measure here is gauge invariant. And just between you and me, imagining that the camera is off, I'm not, I don't have a crystal clear picture of why this is gauge invariant, but I mean, it sort of certainly is. I mean, you integrate over all gauge fields, then you make a gauge transformation, you still integrate over all gauge fields, it's bound to be gauge invariant. There is actually a subtlety, though, which was pointed out by two Japanese physicists about 30 years ago, namely that the matter fields here don't necessarily have a gauge invariant measure, and that leads to something, but I'm not going to go into that now. All right, so this is one possibility: we don't fix the gauge, and in particular, if we were in Euclidean space and we're doing a Euclidean time-ordered product of gauge invariant operators, then over here we'd have a minus s in both places. And that's actually the starting point for lattice gauge theory. Okay. Now the second choice. Yes, I think we have enough time for the second choice. The second choice is the one, since we're integrating over all fields here, and in particular, the thing is gauge invariant, so we've got an infinite factor because we are summing the same thing an infinite number of times. However, we do the same thing in the denominator, so the infinities cancel. Now, on the other hand, if we want to do perturbation theory, it turns out to be better to fix the gauge. And so what we do now is we multiply, we go back to here, and we multiply the numerator and the denominator by a certain factor, and then integrate over the gauge B. Then we make the gauge transformations. All right, so let me just show you what the factor is. The factor is e to the minus I over 2 alpha integrated minus, I don't know why I have minus here because I'm squaring it. Okay, so that's the factor. So we multiply, in other words, we go here and we multiply, well, d lambda. We do that in the numerator, and we do the same thing in the denominator with, say, a d lambda prime. And so what happens, we have this grad A plus Laplacian of lambda prime in the denominator, grad A, divergence A plus Laplacian of lambda in the numerator. But before we integrate over the gauges,
we shift each gauge so that lambda shifts by A0 dot, so that this thing turns into e to the minus I a half integral, and now it is A0 dot minus Laplacian of lambda squared d fourth x, and I'm just a little bothered here because A0 dot, okay. So that is just A0 dot, so this is a number, there's no vector here. Okay, so in other words, we shift lambda in order to, we shift lambda by what? By, we shift Laplacian lambda by A0 dot, and so this changes. And in the delta function, what happens? Well, this thing turns into, oh, well, I'm sorry, the delta function then replaces the Laplacian of lambda by minus the divergence of A in the numerator and the denominator. And the result is that the Laplacian of lambda turns into, this turns into plus divergence of A. Okay, so what are we done with? So we do the integral, we do the gauge transformations, we do the shift, we integrate over the gauges, the delta function enforces this, and what we wind up with is that now this time-ordered product, instead of being this, is an integral O1 ON e to the I s of alpha dA d psi over integral e to the I s alpha dA d psi. And now what is S alpha? Well, let's go over here. S alpha is minus a quarter FAB, that's the part that we knew. In fact, let me write the gauge invariant part. So it's all that gauge invariant part, and then what we have is this term, which is minus I alpha over 2 times that. And if we factor out the I, then what we have is minus alpha over 2 dBAB squared, d4x. And let's just notice that, see, this is DI, AI, and this is D0, A0. So it's all, that's what dBAB is. So now we have an action that's not gauge invariant. It's gauge fixed, but it has this Lorentz invariant form. And so we fix the gauge in a Lorentz invariant way. And what you can show now is that you have time-ordered product of a mu of x, a nu of y, and now this is the vacuum of the free theory, so we're doing perturbation theory, minus I, and it's the Feynman propagator with some suffixes, subscripts, and that is minus I integral a to mu nu over q squared minus I epsilon e to the I cubed x minus y d4 cubed over pi d4. Okay, so that's what pops out. In other words, we recover the propagator that Schwartz was using and the propagator people use when they do perturbation theory, because it's very simple. Eta mu nu is whatever the flat space-time metric is. Now, if you want, we only have about 5 minutes left. Maybe I can sketch how this goes. The point is, if you combine this term with that term, so combine the two, what do you get? What you get is an integral of AB, the D'Alembert, the four-dimensional Laplacian box, in other words, AB d4 that. So that's just some algebra here to show that if you have minus a quarter that, minus alpha over 2 that, oh, sorry, this is for alpha equal to 1. So you set alpha equal to 1 so that it's simple. Combine those terms and you get this. Well, if this is our action, and after all, we're computing this thing where we're doing perturbation theory, so we ignore the matter field. We set Lm equal to 0 and Jb equal to 0. In that case, we're computing, what do we have? We have 4 unrelated scalar fields called AB, except that the metric is funny, because some of them have a plus sign, some of them have a minus sign. The result is then that the propagator then is this. In other words, it's 4 separate propagators. These things don't talk to each other. If this is 1 and that's 2, you get 0. But if both are 0, then you get this with eta 0, 0, which is minus 1 in Weinberg land. All right. It's a natural place to start, but I think we ought to pause and see if you have questions first, and then secondly, if you don't have questions, I'll introduce what may be a new idea to many of you and or some of you, and having to do with Grassmann variables. And so I think it's good to give you one of the ideas and then get serious next week. So first of all, are there any questions about what we did? Let me say, these Grassmann variables, the attitude we take to the Grassmann variables is, well, let me just define them, okay? Let's have one Grassmann variable. The basic thing about it is that its square is 0. And we can think of it as you want, as there are matrices whose square is 0. For example, I imagine 0, 1, 0, 0 times 0, 0, 1, 0. This is certainly 0, 0, and it's also 0, 0. So that's an example of possible representation of the Grassmann variable. I'm not sure what the optimal representation is. Well, if theta squared is 0, then if we do a Taylor expansion of an arbitrary function of a Grassmann variable, it's pretty simple. It's a plus b theta and c theta squared. Well, theta squared is 0, so we're all done. Now you'll say, well, what about the Boron series? What about the 1 over theta cubed or something? I don't know. We don't talk about it. Okay, so now we want to construct a table of integrals. Well, it's obviously going to be an integral of a plus b theta, and we're thinking of a and b as complex numbers, d theta. And so this is kind of simple. This means we have a integral d theta plus b integral theta d theta. So this is, in other words, instead of having a table of integrals that's incomplete and this thick, we just have two. What is this and what's that? All right. Well, the convention is to define them in such a way that this is the same thing as the integral of f of, let us say, theta plus zeta d theta. And that would be what? Well, that would be integral of a d theta plus integral of b times theta plus zeta d theta.
Make sure I've got the logic of this right.
Ah, yes. And now, if we're writing it this way, it looks like one thing, but if we rewrite it, we see we have a d theta, and we have a plus b zeta d theta plus an integral b theta d theta. If we want this to be the same as that, then automatically this term is the same as this one, but this guy is different. So we say this integral is 0. So the rule is integral d theta 0, integral theta d theta not 0. Let's just set it equal to 1. So that's how it's done. And this is something even qubit people could love. All right, so let's quit here then. Unless there's a question?